Welcome, ladies and gents. So up until now, you've been primarily focusing on how a substance evaporates and what impacts the rate of evaporation and how much gas will be present. And that all deals with intermolecular forces. And what we're going to focus on in this video is understanding how the rate of evaporation is going to impact how a substance actually boils. So I know you guys all have probably watched a pot of boiling water at some point in your life, whether you were making macaroni and cheese or making some pasta or maybe ramen or something along those lines. And what I hope you guys maybe can familiarize yourself with is when we watch that pot of water boil, it has really small bubbles to start that are kind of on the sides of that pot. And then we know the water is boiling because we have that vigorous bubbling that's continually bringing the bubbles from the base of our pot up into the surface, and they're bursting with all that water vapor that kind of floats above it in the form of steam. So what we want to have an understanding of is how that boiling process actually happens. So we're going to go ahead and we're going to explain what's going on by kind of writing some words in these notes. All right, so the first thing we want to do is we want to define what this word boiling point is. And I know you guys have heard this in your other classes, but we really want to understand what it means in terms of the chemistry words. So the boiling point is going to be the temperature at which the vapor pressure, which was our new word we learned from that reading, of a liquid equals the atmospheric pressure exerted on a liquid. So basically what that means is the pressure that's inside our bubbles in our liquid, that pressure has to match whatever pressure is pushing down from the atmosphere. Now, typically when we're talking about atmospheric pressure, we're talking about one atmosphere, because usually, when we think of Vernon Hills, we're at sea level. So we will address in a second what happens if pressure changes. But what we want to do is we want to explain how we actually get boiling at standard pressure at sea level. So when we look at a pot of water, you may notice you've got all these little itty bitty tiny bubbles all kind of on the sides and all around the pot of water. Or if you've ever left a glass of water out overnight, you might notice those little itty bitty bubbles. There's a lot of gas already trapped in water, and so those little itty bitty bubbles are present. And what I do is I call them birth bubbles. So the whole process of understanding how boiling occurs is understanding how we can get more and more gas into those birth bubbles. So when we have boiling happen, you guys all know that we have to have some sort of heat source, whether it's the stove, whether it's a Bunsen burner, whether it's, a campfire. There has to be heat that's provided. And so what happens is the heat travels from our source into our water. And so we learned a lot with gases. When we increase the temperature of something, their kinetic energy increases. So that's going to be the first thing that happens. So we've got heat is added to the water, which increases the kinetic energy of the molecules. So that's the first thing we have to do when we have boiling happening, is we have to go ahead and we have to have heat being added to our water to make them move faster. Because we learned in our evaporation reading that in order for us to evaporate, we have to break our intermolecular forces. And that's what has to happen in order for us to boil. We have to be able to break those forces so we can escape from the liquid into our birth bubble. So the second thing that's going to happen is as the number of water molecules with high kinetic energy increases, more water can break. That's the word break. Their intermolecular forces and move into our birth bubbles. So as our heat's being applied, we're going to go ahead and we're going to be able to increase the kinetic energy of all the water molecules that are inside that water. And as those water molecules are moving faster, they're going to go ahead and they're going to have more vibrations, which is going to break those intermolecular forces. Now, because there's these tiny birth bubbles all over the water, they don't have to be at the surface to escape anymore. If they're close enough to a birth bubble and they break their intermolecular force, they can go ahead and they can move into our tiny, tiny birth bubble. So what this is going to do is this is going to increase the number of gas molecules in our birth bubble. So if this is our birth bubble before boiling, we might only have one sad little water molecule in there. As we increase the heat, we're going to increase the kinetic energy. So our birth bubble is going to be able to get bigger and bigger and bigger, because more water molecules are going to be able to break their intermolecular forces and get into this bubble at the gaseous stage. Now we know from gas laws that more gas means more pressure. So as we heat it up and more gas escapes into our birth bubble, our pressure is going to get higher and higher and higher and higher. So eventually what's going to happen is the pressure of our birth bubble is going to equal the pressure of the air, which means we've reached the boiling point. So when we have enough gas particles inside this bubble to equal the atmospheric pressure, we've reached our boiling point. So the bubble will rise to the surface and burst. And so this is happening all throughout the liquid. Everywhere in our liquid, we have these tiny little itty bitty birth bubbles that are going to be able to get more and more and more gas molecules in them as the temperature of our water gets hotter and hotter and hotter, because we have all that intermolecular forces being broken and they can escape into those bubbles. So as we get larger numbers of water molecules into our bubbles, we're going to get them rising to the surface and burst. And so we know that the boiling point has been reached when you have that vigorous bubbling. So this isn't like right away when you see the first couple of bubbles coming to the surface. This is when you see like all the bubbles just constantly coming up to the top and rising and bursting. That's when we know we've reached the boiling point. Now, something really, really, really important to note is you're going to ask me, well, Etnire, how is this boiling stuff different from evaporation? When we define evaporation, it can only occur at the surface of a liquid. So you have to be moving fast enough at the surface of a liquid to break your forces and leave into the vapor phase. Boiling, oh, that's how you spell boiling. Forgot the N there. Boiling occurs everywhere. In the liquid. So that is a huge, 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 huge difference to understand, is because these little birth bubbles are all over our liquid, boiling is taking place absolutely everywhere, where evaporation is only occurring at the surface. Now, if we look at this definition here, which is a really, really important one, you definitely want to make sure you highlight, star, circle, underline this definition here. It's the temperature where the vapor pressure of the liquid equals the atmospheric pressure exerted on the liquid. Now, the boiling point is not going to be the same everywhere on the planet. If you look on like the side of a box of pasta or some baked goods, it will always have directions for baking at altitude. So let's start by talking about that. And what we mean by altitude is we mean like the top of a mountain. So we already learned in our gas laws unit that when we're at altitude, we have less gas present. And because we have less gas present, that means we have less pressure on the top of a mountain. So if we think about this guy up here, that in order for us to boil, the pressure of the bubbles inside our liquid have to equal the atmospheric pressure. If I'm on top of a mountain, I have less pressure pushing down the, oh, that is a terrible arrow. Let's go ahead and redraw that. I have less pressure pushing down than I do at atmosphere. So I may not have one full atmosphere. I maybe only have 0.8 of an atmosphere. Oh my gosh, I'm struggling right now. Ah! So if I have a lower pressure on top of my liquid, that means my bubbles need less pressure to boil. So since my bubbles will need less pressure, that means I can have a lower boiling point. So you're going to have a lower boiling point at lower pressures. Now let's think about something like Death Valley. In Death Valley, you've got more gas present because you're below sea level, which means you have a higher pressure in that area. So if I have a higher pressure in Death Valley, that means I'm going to have a higher boiling point because I'm going to need even more energy to break my forces to get into those birth bubbles. So if we think about this guy here, we would actually have instead of 1 atmosphere, we might have 1.5 atmospheres pushing down on us. So because I've got a higher pressure to overcome, that means my bubbles need a higher pressure. And because they need a higher pressure, that means we need even more heat. So that means our bubbles are going to need more gas. The bubbles need more gas in them to equal the pressure of the air. So since I need more gas in my bubbles, I'm going to need even more heat than I do at sea level. So I would need even faster moving particles in order to get enough gas into my bubble to go ahead and boil. So this is why our boiling point is going to vary depending on where we're at in the world. So that's our lesson for today. Tomorrow we're going to be applying this stuff in a lab setting. So please make sure you review your notes tonight and come with questions for the beginning of class before we get to the lab. Have a great day, guys.